backtrack a little bit. The first section in the textbook that we are supposed to cover is section 1.2, which is on circles. And you may notice that we have not yet covered that this semester. That's because we're doing things out of order. In most of chapter 1, we were looking at functions. And so our focus was really on working with functions. And if I have a circle, that's not the graph of a function because it fails the vertical line test. So it seemed a little bit strange to me that we sort of started with circles whose graphs were not functions and then spent the rest of chapter 1 really focusing our attention on functions. Feels to me like it makes more sense to do this now. We're about to start chapter 4, which is on trig. And in trig, we'll be working quite often with circles, in particular the unit circle, which is just the circle of radius 1 centered at the origin. Okay. And in trig, we actually spend a lot of time working with triangles and a lot of times working with circles. Right triangles are the, in particular, I should say, not just any old triangle. Okay. And at first glance, it seems like these would have very little to do with each other because that's kind of sharp and pointy and that's very nice and round. Okay. But it turns out there are huge connections between circles and triangles, and I'm going to walk you through one of them by starting with a really important property of right triangles. So if I have a right triangle, that just means that one of the angles is a right angle, which means, of course, that it's 90 degrees. Okay. And so then we have two legs, leg 1 and leg 2, that meet to form that right angle. And the third side, which is the longest side, is called the hypotenuse. Okay. And the Pythagorean theorem gives me a relationship between the lengths of these sides. It is necessary that we have a right triangle, okay, but it just says that the length of leg 1 squared plus the length of leg 2 squared is equal to the length of the hypotenuse squared. And probably you're more used to seeing that like so, where we label the legs A and B, and we label the hypotenuse C, and then A squared plus B squared is equal to C squared. I like to start with the version of leg 1, leg 2, and the hypotenuse, simply because there's nothing that says we have to call the hypotenuse C. If I were trying to create a trick question, I could draw a triangle like so, where I said that was C, and that was A, and that was B. Now A squared plus B squared doesn't equal C squared. For this triangle, it would be A squared plus C squared equals B squared. Now, there's no good reason for me to label a triangle that way, but I just want you to recognize that what's important is that the side whose square is equal to the sum of the squares of the other sides must be the hypotenuse. Okay, now what does that have to do with circles? Well, let's take a look at the unit circle, and let's see if we can come up with an equation for it. So the unit circle, I said the center, by definition, is at the origin, and the radius is going to equal 1. So that's the set of all points whose distance to the origin is equal to 1. All right, so if I have a point here, and I call it x times y, I know the distance from xy to the origin. I know that that distance is equal to 1. Okay, excellent. Now, what I can do is I can drop a perpendicular here to the x-axis. And if I do that, I've just created a right triangle where the hypotenuse of that triangle is the radius of that circle. The length of this side would be x, and it's legal for me for this particular point to call that x. Lengths by definition, cannot be negative. So it would be totally fine for me to say that this length is x, but if I had a point over here, let me just draw in another triangle for a point. We'll just call this x2, y2. Now I can drop a perpendicular, and there I've got this side. I couldn't say that the length of this was x2 because x2 would be a negative number because I'm in quadrant 2. But what I could do that would work for any quadrant is I could say the length of this side is the absolute value of x. If x happens to be positive, if we're in quadrants 1 or 4, well, then the absolute value doesn't do anything. But if x happens to be negative, because we're in quadrants 2 or 3, then I'll label this one in green, then the absolute value makes that a legitimate value for a side length. Okay. I can do something similar with the other leg. I can say that the other leg would be the absolute value of y. Okay. So over here, the height of this triangle would be the absolute value of y2. So those absolute values allow me to describe almost any point on the circle with this corresponding right triangle, where the length of the legs are the absolute value of x, the absolute value of y, and the length of the hypotenuse is 1. Okay. So then I can apply the Pythagorean theorem to that. So I can say the absolute value of x squared plus the absolute value of y squared will equal 1. But if I'm squaring these things, the absolute value becomes unnecessary, because whether I square something that's positive or negative, the result is going to be positive. Only time it wouldn't be is if I squared 0. So absolute value of x squared is the same as x squared. Absolute value of y squared is the same as y squared. X squared plus y squared is equal to 1. And that's an equation for this unit circle. So the equation for the circle I derived using the Pythagorean theorem. Now I should mention, I said I can describe almost any point on the unit circle in terms of this right triangle that I can create. There are 4 special points where I'm not going to get a triangle. If I look at the 4 points that are on the axes, either on the x-axis or the y-axis, then if I drop a perpendicular to the x-axis, which is what I was doing, well, for these 2 points, I'm already on the x-axis. And for these 2 points, I can drop a perpendicular straight down to the x-axis. But in all cases, I'm getting what we would call a degenerate triangle. I'm just getting a line segment because x, if I'm going straight to the right, I'm not going up at all. My y value is 0. So for this point, the height of my triangle is 0. For this point, it's like the base of my triangle is 0. So I'm really not getting a triangle at those points. But let's just take a look. I know if this point is on the x-axis, that means its y value is 0. And I know that this distance has to be 1 because it's on the unit circle. So that's the point 1, 0. That satisfies this equation. So this equation works even for that point, even though I don't think of it as the Pythagorean theorem when I'm applying it to this point. This point up here, we're on the y-axis, so now the x value is 0. Looks like we've come a distance of 1 up, so that would be the point 0, 1. That also satisfies this equation. This point here would be negative 1, 0, because we've come a distance of 1, but we've moved to the left, so our x value is negative. That satisfies this equation, and this point down here would be 0, negative 1, and that satisfies this equation. So this equation describes all of the points that are on the unit circle, and we'll be working with the unit circle quite a lot as we work through chapter 4.